Okay, we're going to look at finding the domain of the following radical function. And I want you to notice right away what type of index that you have before you proceed. So keep in mind, we see f of x, we do not see the index written. So it is implied that our index is 2, and that is an even number. And if that is the case, we do know that we'd have to set the radicand greater than or equal to 0 in order to find the domain. So in our case, the radicand is 36 minus x squared. So 36 minus x squared greater than or equal to 0. And I'd also like to point out this radicand, or just to kind of really interpret this inequality that you're going to be solving, it is not a linear inequality. We actually have ourselves a quadratic inequality. So the way we would solve something is a little bit different than some of your previous examples. It takes a slightly more work to figure out what the solution to this quadratic inequality is. But lucky for us, we have those techniques, and that technique would be using the sine analysis method. So we're going to take it a little off to the side if I'm going to go through this as far as using the sine analysis method. The first thing I need to understand is finding my boundary points are. And that's found by taking the inequality and replacing the inequality symbol with an equal sign. So now we have ourselves a quadratic equation, and we can see if it factors. I do see that x squared, and I see that 36 is a perfect square. So I really like that it's going to have a difference of squares. Now be careful when you factor with difference of squares. The 36 is first. So that means when you break it down, the perfect square, or 6 times 6 is 36, that comes first in each of the binomials. Now we'll have the x split up, and with difference of squares, we have a plus 6 plus x and 6 minus x, giving us 0. So solving the resulting linear equations from this quadratic factorization, 6 plus x equals 0, 6 minus x equals 0. We should get, subtracting 6 on both sides for the first one, x equals negative 6, excuse me. I'll write that a little nicer. Or here, might be easier to add x to both sides. So I get 6 equals x, or x equals 6, same thing. So now we have our boundary points. And remember, with our boundary points, we would plot our boundary points on a number line. Looks like we have negative 6 and positive 6. Separate the number line into 3 regions and include our factors on the far left. So I have 6 plus x, 6 minus x. Then we would pick a test point in each region. So if I'm picking something to the left of negative 6, let's say x equals negative 10. 6 plus negative 10 is negative. Be careful on this next one, 6 minus x. This would be 6 minus a negative 10, which would then be giving us a positive 16. So be very careful. Sometimes I write it out if I have to think about it. I then pick another test point. I'll be picking 0. 6 plus 0 gives me positive. 6 minus 0 also gives me positive. And then I'll pick something that comes after 6. I'll test x equals 7. 6 plus 7 is positive. 6 minus 7 is negative. So now we'll take this and we will multiply the signs vertically. Negative times positive is negative. Positive times positive is positive. And positive times negative is negative. So now we have our regions. We go back to our inequality that we were trying to solve. We look at the fact that it's compared to 0 as greater than or equal to 0. So this is reminding us we need to find where do we have positive regions. And right away, we just see that it's in between -6 and +6. So the solution to this inequality is -6 to +6. Excuse me. We have greater than or equal to, so I have brackets. Now, the question remains, why did we solve this inequality in the first place? Well, we were trying to find the values of x that gave us a positive radicand, or equal to 0. So the solution to this inequality is actually what you're trying to find. So if we're trying to understand this, what we would say is, who is the domain? Well, you can list it in the interval notation that you found. Or if you prefer set notation, that would be x such that x is in between the two numbers. So that's a very nice way, accurate way to figure out your domain. I would like to call your attention to just kind of looking at the graph to see if what you have analytically matches up with what you see. So let's switch back to the TI just to inspect or investigate a little bit more. And I'll go back and I remember I'm looking for square root. So it's the square root of 36 minus x squared. That's x times 2, so let me make sure that's an exponent. There we go. And what we can do is we can graph it, and you can kind of see you have it looks like a half circle. And so as you're inspecting the graph, you could kind of see, oh yeah, it does look like, it looks like there's some stopping points. It does look like there is a function located in between the values of -6 and 6, but once you go on beyond +6 or beyond -6 in the negative direction, there's no more function. So this does help us justify, oh yeah, our analytic solution really does match what we see in the calculator. However, it doesn't work the other way around. If you see this in the calculator, you can have an estimate of what your domain would be, but you can't be clear about where those boundary points actually stop and start. So, it might be really close to the number 6. So I always recommend for you to follow up. If you think it's something, most likely you might be correct, but there are some chances where you need to prove analytically what that domain really is. So I hope this helps. Just kind of be paying attention. Remember, there's a difference between having a linear inequality versus a quadratic inequality. And if you can remember that and understand that you're only dealing with this when you see even indices, then you're going to be in good shape. So I do hope this helps. I will see you next section.